For this video, we need to prove using the definition of a limit of a sequence, the limit of the rational expression 2n over n plus 1 as n approaches to infinity equal to 2. Again, as mentioned, we are going to use here the proof per definition. The definition for the limit of a sequence, or whether a sequence converges to a certain number which we call limit, if for every epsilon there exists a natural number k such that for all n greater than that k, the terms x sub n of our sequence for this definition satisfy the absolute value of the sequence x sub n minus x, which is the limit, is less than epsilon. So we need to establish this for us to say that the limit of the said sequence here, 2n over n plus 1, as n approaches infinity, is really equal to 2. Before we start, we could use this idea to target our guide, or what would be our target expression later as part of our proof, as we substitute here our sequence 2n over n plus 1 minus your limit, which is 2, must be less than epsilon. Let's try to solve this in terms of n, so we could use this as a part of our proof later. So that would mean we will have here the absolute value of 2n minus twice n plus 1 over n plus 1 less than epsilon. Okay, so you will have here 2n minus 2 over n plus 1 should be less than epsilon. So you will have here the absolute value of 2 over n plus 1 must be less than epsilon, which will give us the expression of positive 2 over n plus 1 less than epsilon. If we could reach this idea later, then we could actually, that's already a proof, or a part of a proof, that the limit of the given expression is really equal to 2. But let's not stop there. Let's end to our target expression, which is part of our proof. It would be an expression with n on one side. That would mean we are going to multiply both sides by n plus 1 over epsilon. So you will have here 2 over epsilon is less than n plus 1, or cross multiply if you would like to. And in terms of n, you will have here 2 over epsilon minus 1 is less than n. This will be used later on because this is just derived to this expression. Once we were able to establish this as part of our proof, then ultimately it connects to this idea, which is the definition itself. So let's look into that later as we go back here and we start with our proof. So part of the proof is to introduce an epsilon, no matter how small it is. Our epsilon is greater than 0. And with this, after that, we are going to assume a certain value of k. So let's have this and k be equal to this target expression here. Okay, this one here. You cannot see that because my pen is white. So this here, this expression, 2 over epsilon minus 1. So let's have that. Okay. So you will have here k is equal to 2 over epsilon minus 1, element of the set of real numbers. Of course, we cannot guarantee that k is a natural number, but since the definition requires us for it to be a natural number, so we'll have here then n is only greater than k, because it would not be equal to k, as k is strictly a natural number. Because if we are going to have n is greater than k, which is equal to 2 over epsilon minus 1, then we can say that this implies, okay, that n is greater than 2 over epsilon minus 1. Okay. Now from this, we can just simply rearrange or manipulate this expression in terms of, so that we could get an expression equivalent to epsilon. So this would become, we have n plus 1 greater than 2 over epsilon. You could see that it is almost similar to what happened here at the bottom, but of course that is done as a scratch, or a part of the scratch, to guarantee that we know what our target is. So after this, we can now say, okay, by cross multiplying or multiplying both sides by epsilon over n plus 1. So you will have your epsilon is greater than 2 over n plus 1. Or you could say that 2 over n plus 1 is less than epsilon. Now that we reach this, let me change my color to black. We can now start. Hence, for n is greater than k, we have, okay, we will be using this expression here, which is just the same as this expression here. Okay, so you will have this, the absolute value of 2n over n plus 1 minus 2, which is equal to 2 over n plus 1 less than epsilon. Cutting the middleman, we can now say that the absolute value of 2n over n plus 1 minus 2 is just less than epsilon. And then we have achieved the definition. Therefore, we can now say that the limit of the sequence 2n over n plus 1 as n approaches infinity is equal to 2, because we have established this already. This is the end of the proof. You could see this a little bit shorter than before because we're able to guarantee this expression here. So it's very important to start with the target expression by the definition, and we are going to use this as our expression k here, which will be used later on in the process. And as we manipulate, you could see that it will, the sum expression will just return to expressions here. That's your proof that you're doing it right. And once you have established this, definitely you cannot claim your conclusion. Thank you very much for watching.